So um, the tool already mentioned there's the GitHub um, repository, and we have the link in the chat there that shows some resources. Um, and so if you see that here, resources, the first one is slides. So I'm going to use these slides, and if you want, you can open those up as well and follow along on your computer. Okay, so the title of today's talk is Modular Reproducible Workflows with the Targets R package. Uh, yeah, again, my name is Joel Nitta. I'm a project research associate at Tokyo University. I study ecology and evolution, particularly of ferns. Um, and I'd say my hobby is running. I used to run marathons, but these days it's more running after my 6-year-old. So for today's talk, it consists of two main parts. First is going to be an introduction to the targets package, and then some live coding to show you how that works. And then in the second part, we're going to delve into the details of how to use targets specifically for bioinformatics. And I'm going to, at the end, show a demo of how to do that with a workflow that I actually wrote to do variant calling. And I'm hoping that everybody who's participating today has already done the prerequisites of installing R Studio and targets. And also for part two, you'll need Docker and Conda as well. Okay, so the first part. So why should we use the targets package? Well, the simple answer is to make your code more reproducible. So what is reproducibility? This is my own definition. I would say it is the ability for others or your future self to rerun your code and get the same results. And I think there's a little bit more, however, there's a little bit more nuance to this. It's not a simple yes or no proposition. As I've been doing this, I've kind of come to the realization that reproducibility is more like a mindset. It's something that we're always striving for, but maybe it's not possible to ever get it perfect, right? And it has many aspects. Of course, like we're going to be talking about today, it involves writing code, but it also involves things like maintaining your computing environment, making sure that your data is available to other people, and like the last option and the last one here, code automation, and that's where targets package comes in. And in fact, we'll get more to computing environment later in part two. So a typical workflow in R looks something like this. This is a figure that probably many of you are familiar with. It's from Hadley Wickham's R for Data Science book. And it typically, a workflow will involve something about importing data, tidying it into a format where we can analyze it, maybe transforming some of the data, and you'll build models, visualize it, and at the end you'll communicate results. And so typically we'll have a series of scripts that do this. But if you write all of those scripts out and you don't have any master script to control it, then you have to remember what steps need to be run in what order. And furthermore, if one part of that workflow changes, it's hard to know how it's going to affect the other parts. So if one part of this changes, how much of it do we need to rerun to make sure that everything is up to date? If it's a small workflow, maybe you just rerun everything and you don't have to worry about it that much. But if some of these steps are really memory intensive and take a long time, then it can be have a huge impact on your productivity. And so that's where workflow automation comes in, and we're going to be using the targets R package. So it's the biggest feature is that it takes care of all of this orchestration for us, and if something changes, it will only rerun the necessary steps. And it comes with some other really nice features. For example, it can run workflow steps in parallel and then speed up your analysis. And overall, this provides proof that the results that you're showing are derived from the code that you wrote. Now, we're only going to be able to get into the basics of targets today. And so I've given some resources here to help you learn more about it in the future. And especially, I recommend, of course, the targets package, or excuse me, the targets GitHub repo at the top there, as well as the package website, and the user manual in particular is really informative and well written. And the developer of targets, Will Landau, is fantastic, and he's really responsive, and he's always pushing out updates. And if you go to the GitHub repo, you'll find a discussion area where you can ask questions, separate from actually posting issues. You can just ask questions about something that you may be not sure about, even if it's not like a bug. And he's almost will always, give you a helpful reply. Now, in addition to the targets package, there's actually a couple other related packages, and those are collectively known as the Targetopia. This is somewhat akin to the tidyverse, which is a collection of packages. Okay, good. Are we all still here? Okay, my monitor froze up for a second, but I think we're good. Okay, I'm just going to mention one right now. It's called the T archetypes package or Tarchetypes package. And that's one that often gets used. And I'll explain a bit more how that works later. So just I would make a note of that. That's another sister package to targets that you'll be using frequently. And then, of course, here's the discussion board that I mentioned. All right, so I think the best way to learn targets is to actually get your hands messy and start doing it yourself. It's hard to really get a feel for it if you're just hearing a verbal description. So that's why we're going to switch over to live coding, and we're going to learn about some of these basic functions. So these are the functions we're going to be covering. Tar script is a template function that generates a generic workflow script. Tar viz network visualizes the state of the workflow. Tar make is really important. That's going to run the workflow. Tar load loads the target that's been built from the workflow into your environment. And tar outdated can list which steps will be run next time. And you'll notice that all of these functions begin with tar underscore. And that's just a convention so that you don't have namespace collisions between functions that might be named for like make or load from another package. All right, so with that, we're going to switch over to the live coding. So give me a moment here to switch to RStudio. Screen share, RStudio. Okay, so I hope everybody has RStudio installed and running right now. And if you do, you should see something that looks somewhat similar to this. So for any data analysis, I prefer to do it in a project. And a project is just a given folder that corresponds to a certain data analysis project. So we're going to use the RStudio projects feature to do that. So let's see. Unfortunately, you can't see my file menu since I'm sharing my. Let me switch to sharing my screen, and hopefully that'll work better. Just a moment. Share. So
Take your time.
See. Okay. See the file menu. Okay. Okay. How's that?
Yeah, we see it now.
Okay, so if we go up to the top and click on File, and you go to the second option, which I know it appears small here, but I think you should be able to see this on your computer. It says New Project. So we'll click on New Project. I think, do I need to? Oh, okay, it was just thinking. There it goes. So we get the New Project wizard. We're going to click on New Directory. First option is New Project. And then we choose a place to put our project. Again, this is just a folder that we're creating. And I'm going to put it on my desktop, which is the default location here. And I'll name it Targets Demo. Okay. And if you need to put it somewhere else, you can click this Browse button to put it somewhere else. But I'm going to go ahead and put it on my desktop. And I'm not going to use Git or rm with this project. But those are both really important options that you probably should do for a real project and not just a demo. So we'll hit Create Project. So now it's opening that up. Okay, and this is what a new project looks like. And we haven't done anything yet, so our environment is empty, and the file browser here, now we are in that folder, and it just contains one file, which is this .rproj file. And you don't normally edit that by hand. That's just our studio's way of knowing that we are in an R project. Okay, so now that we've done all that, we're going to go ahead and get started with targets. So we'll load the targets package with library. So there it goes. And that first function that I mentioned is tar script. So let's type that, TAR underscore, and you can see RStudio is doing the autocomplete there. So I'll choose that option, tar script, and hit return. Okay, what happened? Doesn't look like much happened, but if you look at the file browser on the right, you'll see that we have a new file called underscore targets.r. So let's click on that. Okay, so now we have opened this underscore targets.r, and I'll rearrange this so we can see that a little bit better. Okay, so it says some comments. This is an example underscore targets.r file. Every targets pipeline needs one, and so that's it means exactly what it says. That's a really so this underscore targets.r file is a special file, and targets won't work without it. You can change some settings to name it differently, but that's the default. Okay. So let's have a look at what's in here. It starts off with a call to the loading the targets R package, like we just did with library targets. It's got a function definition that's defining some custom function. This tar option set, which sets options for targets. And then at the end, it's got a list. Okay. And this is really important. Underscore targets.r file always has to end with a list. So what is this list? Well, this list defines your workflow. Okay, so this tells our what things we want to build during our workflow. And when I say a thing in the workflow, target's name for that is a target, right? So we're building targets. And you'll see that the list of targets, each of those is defined with the function tar target, right? So this is another really important function, the tar target function. That's how we define the targets that we're going to build. And the tar target function has some more arguments, but the first two are the ones you really need to remember. Okay, the first argument of tar target is the name of the target that we're building. All right, so we have here we're building two targets. One is called data, and one is called summary. And the next part of that function is the function that R uses to build the target, right? So data is going to be built by the function data frame. And then summary is going to be built by the function sum, which takes data as its input. Okay. And if we look at what's going on with what is this data, how is that going to be built? So it's data frame, which is a base R function, and it's got so that's going to build a data frame, and it's going to have two variables, x and y, and each of those are going to be some random numbers, well, 100 random numbers between 1 and 100. That's built with the sample.int function. Now, you might not use the sample.int function very much, so let's see what that does. Okay, sample.int, say 10. So what that does is generate 10 random numbers that are between, we'll send 10 random integers that are between 1 and 10. Okay, so this will generate a data frame that's 100 rows long with x and y, right? Now, what about this sum function? Okay, let's ask for some help about sum. Nothing there. Where's that? Okay, so that is this function that got defined up here, right? Earlier in the script. So this is a custom function. And if you're not used to writing custom functions, that's another thing that's a little bit different about targets is that it makes extensive use of these custom functions. So you'll get a lot of practice doing that with targets. So the sum function, it takes a data set as input, and then it's going to use the base R summarize function to calculate the mean of x, right? So I think now we have a pretty good idea of what this is going to do. So let's run the workflow. So we do that with tar underscore make, okay, and hit return. So you see it's thinking there, start target data, build target data, start target summary, build target summary, and it's done. Okay, so it ran the pipeline. And of course, it didn't take very long. So let's see what summary is. Okay, so type summary and then hit enter. Okay, that's a little bit odd. It says as a function. What about this summary? Well, the thing is, even after you run targets, it's running in a separate, independent R session instance of R, not our current instance. And the reason for that is when you run a targets pipeline, you want it always to be in a completely clean environment without any variables that may have been added that aren't in the code, right? Um, so it's designed that way for a reason. So we have some separate functions that we need to use to um, access this. Okay, so that is the tar load function. So type tar load, summary, and hit enter. Now you'll see in the environment pane we have some data showed up, summary. Okay, so if we type summary now, okay, that looks more like the data we were looking for. We have the mean of x is 50.5, which is about what we would expect. I think our random number generator is working correctly. Okay. Um, so is there any questions up to this point? Let's see. Oh, I see there were some questions. Okay. Glad we got questions sorted out in the chat there. Okay. Um, so you may be wondering, targets can do all this stuff, but where is this, right? Where are these data that it's storing? Well, if you look over here in the file browser, you'll notice there's another folder that showed up, and that is this one called underscore targets. Okay, so this is where the targets R package stores the data that it's calculated, and that way it can actually store it across R sessions, right? So if we were to let's restart R, okay, session restart R. So I've restarted my IR session. My environment is empty. I'll load the targets package again. Oh, library targets. There we go. And I can let's see. If I type data, again, it's a function and not the data that I wanted. But if I say tar underscore load data, now we have, I can look at the start of that data frame, right? So these data that targets has calculated persist across our sessions, and the way that works is because it's storing them as files in this folder called underscore targets. So we can have a look at what's in there. I know this is going to appear quite small. Let me see if I can maybe make it look a little bit bigger. Just a second. Share. Just a second. Okay. That should look a little bit bigger. So if we look again, we're looking inside the targets folder. Okay. You'll see it has a git ignore file and then 3 more folders. And typically, you never need to worry about what's in here. I'm just going to show you this objects one. Okay, so if you look in objects, you'll see here are those targets that we built, data and summary. Now, again, it's best not to mess with the internals of targets because things can break and your project will not be reproducible. But at least you know where you can find these things if you need to. But there is one more folder that you will use, and that's called the user. And it's named that way because it's the folder the user uses. And right now it doesn't have anything because by default it's empty. But you can put anything you need to in there. And in the second part of the talk, I'm going to show you how we use that to store output files and intermediate files in a bioinformatics workflow. So we will come back and use the user folder but we don't need to worry about these other ones. This is just to let you know what targets is doing sort of under the hood. Okay. So, okay. Um, so as I mentioned, we had quit R, we started R again. So let's see what happens if we run tar make one more time. R underscore make. Okay, when we ran tar make again, this time it didn't do anything, and it tells us that it didn't do anything. It skipped these targets, and that's because none of this code has changed. So targets is tracking all of our code, and it knows that nothing's changed. It knows that nothing needs to be run. So that's really nice, because if these were not these very simple functions, but more complicated things, this could save us a lot of time. All right, so let's see what happens when we do change something. For example, maybe I don't want to know the mean of x, I want to know the minimum of x. Okay, min of x. Let's change that way and hit tar make. Okay, wait a minute, it skipped it again. Why? Well, the reason is because I didn't save the file. And remember that targets is always running in a new session of R, so it's loading that file from the over again, right? So we need to always make sure you save it, Control or Command S, before you run it. Okay, so let's try that again. Save and then tar make. Okay, now you'll notice that it skipped target data because data has not changed. But we changed the summary function, so it noticed that and it reran summary. So if we do tar load summary, and we take a look at summary, now we see the minimum value, which is 1. Okay, um, so that's an example of how targets works to detect changes in your pipeline. Now another another related function that you might use to inspect your data is tar read. Okay, and what tar read does is so tar load actually loads this target into our environment, right? But tar read is sort of like read line or read CSV, all these other read functions that that load the data. Let me see how. Well, I'll just do it. Then it's easier to understand. Tar read summary. So you'll see there, it just printed it out directly to the screen, right? So if we were to remove the summary object in R right now, now it's gone, and we do tar read summary again, you'll see it just prints out directly and it doesn't actually load it into the environment. So again, that is sort of like how something like read CSV or read lines would work, right? So you could save that to a different variable if you wanted, right? And then we call it A, something like that. Okay, so tar load, tar read. All right, so another really nice function or feature of targets is workflow visualization. So we can do that with the function tar viz network. Tar viz network. Oops, I don't have that installed. Yes, let's install it. So this requires a separate package. I recently updated R and a lot of my packages are gone. So that'll take a second. But what that's going to do is show us an interactive network of our workflow. So let's try that again. Tar viz network. Okay, and there it is. So you can see that it's showing that it moves from left to right, right? So you can see that showing the output of is summary, and that depends on two things. It depends on the data target as well as the sum function. So the word stim here refers to targets that are built during the workflow, and it also has it as well as it also tracks functions, right? So, and the dark green shows that it's up to date. So if we were to change something again, let's change, how about this time the data generating function? Say that to sample integer over 10, okay? and command save, and then tar viz network again. Okay, now we notice that it changed, right? So you will see that this color changed. Now data is this teal color or light blue because it's outdated. That means it's going to run in the next instance when we run targets, as well as summary, because summary depends on data, but sum has not changed. So if you do tar underscore make, runs, builds it, and then let's visualize the network again, and we're back up to date. Okay. So that's really nice, especially if you're working locally and you can run this in RStudio and get this really handy graph. Now, you might, especially for um, uh, if you're working remotely over a server, you might not have access to a GUI, right? So you might just be using the command line. And in that case, another function is handy. It's called tar outdated. And this will show you, well, we're up to date now, so there's nothing to do. But if we were, if we had changed something, so again, I'm just going to keep on flipping back and forth here, but to make targets go out of date, but change this to back to 100, and then run that again. It'll tell us a character vector of the things that are outdated. So that's a nice way to check what is going to be run the next time before you do it. Because again, if any of your steps are really memory intensive, you want to know about that before you run the pipeline. Okay. Check the great. There was one other important function that I want to mention because we're going to come to it later is so far all of this has been done in R, right? Pretty much everything is encapsulated in this one script. But what if, for example, we need to tell targets to read in a data frame that's external, right? How would we do that? So to show you how to do that, I'm going to go ahead and write this data to an external file with write CSV data CSV. Okay, and so we go back to our files pane. Now we've got some data that we're going to tell targets to read in. Okay, and for that we actually need to load the we need to use the tar archetypes package. So if you haven't installed it yet, you can install that with install packages tar r, and I always misspell this, archetypes. Okay, there we go, tar archetypes. And we'll add that to the top of our script, library tar archetypes. And we're going to use a function from tar archetypes called tar file. Okay, and tar file. Oh, let me load tar archetypes so RStudio knows about it. Okay, so tar file, you'll notice is a little bit different from this. So the tar underscore target is sort of the generic function for defining targets. But there's some other sort of specialty functions that you can use for different target formats. Okay, and so this is for the file format, right? So here we're going to call it, let's call this data from file. Okay, and we're going to say, actually, excuse me, let's call it data path. Data path, okay, because this is going to be the file path, and we'll call this data dot, or excuse me, and we'll run that with data.csv. Okay, so we can do that. Let's go ahead and do that, and I'll and run tar make again, tar make. Okay, so it did all that, and tar viz network. Okay, so you'll see that we have data path, but it's not actually connected to anything yet. So it's off here by itself in the network. And if we look at that, let's see what it is. Tar read data path. It is just this path, data.csv. So that seems kind of unremarkable. But what we can do with that is, for example, say target about, let's define, so we'll pretend that we didn't have this, okay? We're not going to use this line anymore. We're going to read data in from this CSV file, okay? Read.csv data path column, okay? Hit save and tar viz network. So now you'll see that in our network, data is depending on data path, right? And then that's flows into summary. So if we run that tar make, now it runs. Okay, so what's going on here is, so we use read.csv to read in the data from this path. But the really important thing is that if we were to go in to data.csv, view file. So here are our data in a CSV format, and change one of these values. Make it really big. Hit save. Now, if we say tar make again, okay, it ran it again because it detected that the CSV file changed. Okay, so that is why tar file is really important, because it detects changes in files. All right, if this was done simply with tar target, it would not have seen that change, because it would only know about this character vector and not the file that it points to. All right, does that make sense to everybody? Oh, and we have a question. Is the targets package able to perform a snake make like dry run of the workflow? So I actually am not familiar with snake make. I haven't used it, so I'm sorry, I'm not sure about what a dry run would do. What it can do is to tell you that tar outdated. You can use tar outdated, which will tell you if there's any targets that have not been built yet that will need to be built. And you can do the tar viz network to see what the workflow looks like. I'm not aware of anything else beyond that that would be a dry run. All right. But yeah, but that is a great point, is that SnakeMake is another really good workflow management system for Python that you may prefer to use if you work in Python. This is mostly for people who maybe already are working in R and would want to do this in R. All right, so this has all been if the workflow is properly described. Okay, so targets does do some tests. So for example, if I didn't uncomment this and try to run it again, say tar make, it's going to issue an error because there is duplicated target names, right? Since this is a network and every node needs to have a unique name, right? So it won't allow you to have duplicated names. So it'll conduct some tests before it runs the pipeline, and if anything's wrong, it will tell you. Okay, so we don't want that. Okay, so this is all, of course, very low level explanation of the functions, so you can see how they all work. But it's also useful to see how this might work in a more complete workflow. So I'm going to give you a quick demo of that. Let's see here. Yes, thank you for the question. Questions are always appreciated. Just a moment. So that'll be it for the live coding. Now I'm going to switch over. And again, this is a summary of what we just covered. So I am going to show you, though, a quick demo of another workflow And we're not yet to the VCF workflow. We're going to get there, but this is just to show in a bit more detail how targets works. So you can click on this link in the slides, which is an example repo on my GitHub, targets gapminder example. So I'll go there right now. And so these are all the files in the repo, as you can see in GitHub. So if we click on targets.r, so I'm just gonna show this in here instead of actually running everything in RStudio, right? For one thing, you'll notice that I don't have functions defined here, right? I have separate scripts to load both packages and functions, all right? So when you write a real workflow, it's best to have the underscore targets.r file mostly just define the workflow, and you keep the functions defined somewhere else. And so this is actually a lot like writing an R package, that a lot of the content is going to be a bunch of functions that are defined either in separate files or in a single file or some mixture of that. You can do whatever you want as far as that goes. I prefer to put them all in one file that I call functions.r. Okay, and so here's the workflow plan. And this demo is actually analyzing a data set called Gapminder, which is some economic data for many countries across the globe from like the 1950s, I think, to 2000. So it loads the data and then does some tidying of the data, and then it fits a model, and then it reports the results. So when you have your workflow defined like this, it is both the code that runs everything as well as an overview of what's happening. Oh, thanks for typing in the link there, Batul. Now, another feature of this is you'll notice, if you look in detail here, I'm fitting a life expectancy by year model for each country in the data set, but I only have a single target. And that's because you'll see that this target includes this argument called pattern, right? It says pattern map gapminder. And what's going on there is that I actually have, in the previous step, I grouped the gapminder data set by country. So this is similar to like dplyr grouping and mapping. So we have it grouped by country, and then when it runs this function, it's actually doing that one country at a time, and each of those countries is its own target. So this is a way of defining over 100 targets with a single function call, okay? And because those are all different targets, and they're all basically, and none of them depend on each other, they're all depending on the same gapminder data set, those can be run in parallel. So you can tell targets to run that in parallel, right? So again, that's a really nice feature of targets, is that it can save us time by parallelization at the level of the workflow. You don't have to do it. You don't have to write any special functions to do that. Targets will do it for you. And if we take a look at the functions folder, the functions file, so I always put my other R scripts in this R folder. So I have targets is in the top level, and then I have a folder called R, and that's where I put functions and packages. So we take out functions. This only contains one function, but this is the one that fits that model, which is a linear model life expectancy by year, to each country, right? And I always like to use the RStudio has a built-in helper to populate function documentation like you would for a package. It has a package function skeleton button, and that's really useful for documenting your functions, because again, you're going to be writing a lot of functions. Okay, so that's just an example of a more realistic targets workflow. Are there any questions at this point? All right, if not, I'm going to go ahead and move on. Well, let's see. Okay. Yeah, if not, I'm going to go ahead and move on to part 2. Okay, and in part 2, we're going to get into the more bioinformatics side of things, right? Okay, so how can we use targets for bioinformatics? Well, targets was originally designed for workflows in R, where everything can be done within R. Um, but for bioinformatics, typically we need to use other software packages, right? Um, so this is my sort of scheme for doing that. And this looks like a lot of details. So I'm going to go through all of this in the next series of slides, okay? First of all, the input for a bioinformatics workflow, typically the input and output of each step is a file, not an R object, right? And we're gonna use that tar file function a lot, and we're gonna use wrapper functions to call other programs from R. We're gonna use Docker containers to run these external programs, and then we'll maintain our R environment with Conda, and we'll maintain our R packages with our env. Okay, so if you put all that together in a diagram, that's what this looks like. So you can maybe come back to this. And again, I'm going to go through all these things right now in more detail. Okay. Okay. So another feature that of a bioinformatics workflow that's a bit different from a typical targets workflow is, again, we're working with files a lot. And I have a preferred place for storing all these files, and that is in the targets_target/user folder. And the reason for that is that it actually allows us to snapshot our workflow state with another package in the Targetopia called get targets. Okay, so get targets is really nice because as we saw earlier in the targets hands-on demo, targets will always rerun. When you run tar make, it'll only run the steps that need to be run to get the workflow into the up to date, right, to match your code. But as you saw, when I went back and changed something to, so if I changed my function that defined the data frame and I flip back and forth to an earlier version, even though targets had run that before, it doesn't remember that. It will need to rerun it again. Okay, so that didn't matter for a tiny function. But if there's a long running step and we go back to a previous version and target needs to run of the code and target needs to rerun it, that can take a lot of time. So get targets will actually snapshot the target's cache for us so that we can roll back to a particular step and not have to rerun everything, all right? So I think this is really handy for bioinformatics pipelines, and I'd recommend you use it. It's sort of like an extra safety net in case you change something inadvertently. I don't have the time to go into detail about how to use that today, but there's a link here on this slide, so you can check that out. All right, so a little bit more detail about how to set that up. This is my preferred way to do it. You can do it however you want, as long as your folder organization makes sense to you. But my way to do this is to have 3 folders, well, higher level folders in user, data, intermediates, and results. So data are the raw data files. Intermediates are input and output of intermediate steps. And then the results are the final output, such as maybe your manuscript. All right, so those are some tips about working with files in targets. Okay, so the functions that we're going to write to do a bioinformatics workflow are often going to be functions that call external programs, okay? And in R, there's several ways to do this. And I've listed some of them here. The most basic one is called system. And when you run system, you just type in exactly what you want to do in the shell is its argument. It's very simple, but is somewhat limited in what it can do. System 2 is a little bit more complicated. And then there's also, and has more features. And then there's another one from a package called processx called run. And this one has by far the most features. You can set up asynchronous processes. You can specify a different working directory from where you are currently. You can redirect standard out. Oh, excuse me, one of those should be standard out, standard out and standard error, and some other things. And the way this works is I've shown the syntax at the bottom. The first argument is the command that you're going to run, and then the second argument is the arguments to that command. So for example, if you were going to run the ls command to list things in your environment, it would look like this: ls, and then a character vector where each element of the vector is one of those arguments for ls, right? So that is part that make you a bit tripped up, is that, and maybe I'll demo that in our studio here. So if we were to say system, this is the basic system call, ls-l-h. You just type everything as a single character string. Okay, hit enter. It lists the files that I have there. But if we do that with, I'll load library process x and do run, we have to type it like this: ls and then a character vector, right? Dash 8, or doesn't matter the order, but dash h, and hit run. The other thing about process X is it actually, instead of spitting out the results directly to the screen, so this is the standard out that just gets printed out to the screen by system. But with process X, it returns it in a list, and it returns the standard out as a vector instead of catting it. So the vector, our line breaks show up as a \n here. Okay, so those are some differences. So process X, it may just seem more complicated, like why would you bother with that? But it is really useful, especially because it has this ability to specify a different working directory from where you're at. So in R, in your R scripts, you generally don't want to change your working directory. That will often just cause confusion. So if you need to tell a program to run with a different working directory, you can specify that in process X. Let me see. Check the help. Yeah, WD. So if we were to say run ls and say WD equals underscore targets, it'll show us it'll run ls in the targets folder, show us what's in there, and we didn't have to change your own working directory. So that's actually really useful, because different bioinformatics programs will often make assumptions about your working directory and assume you'll just change in there with WD or CD, but we don't necessarily do that with R. Okay. All right, so yes, we're going to use process X run to call external programs, but we're actually run those programs with Docker. All right, and I'm assuming that everybody has some degree of familiarity with Docker here, because I can't go into all the details today. But basically, a Docker container is a lightweight, standalone, executable package of software that includes everything you need to run an application. Right, that's the definition from the Docker website. And so the key point here is that a Docker container is basically an isolated program that can be run by itself, and you don't need to install its dependencies or install it on your machine locally. And this is a lifesaver for bioinformatics workflows, because, as I'm sure you all know, if you've tried to install custom software, just doing that can take all day or many days, and you're like really frustrated because you just want to run something and you can't because you're wasting time trying to deal with dependencies and dependency hell. But Docker makes that all go away as long as there is a Docker container to run it. Okay. So this is an example of how that might work. This is a Docker image, the name of a Docker image for a program called FastP. And if we have, as long as we know this name, we can give that to Docker, and it will run FastP for us, and we don't have to install it ourselves. So you'll notice that it's got a couple different parts to it. That's the name of the program, and then it's got this colon here, and the part after the colon is what's known as the tag, and that includes information about the version. Okay, so not only do we not have to install FastP ourselves, but it is also we know explicitly which version we're using. So that's really important for reproducible code, so that if if somebody else wants to run this program, as long as they use that same Docker container name and tag, they'll be running the exact same version of FastP. So we don't have to worry about differences between different people because of different versions of code, right? So instead of installing FastP from scratch, I can use this Docker run command, which will then run it. Okay, so I'll go ahead and demo that right now. Command copy, bring up the terminal. I'm gonna make my, excuse me, oops, clear this out. Okay, make my font a bit bigger. Everyone see that now? Okay, so if we say, why don't we change up to the desktop? Okay, clear again. Okay, so if I type, I'm just gonna copy paste this. Okay, Docker run. So I didn't provide FastP with any data or anything, so it just spits out its man file. But you can see that it did run correctly, right? So, and if you do that, you should see the exact same thing. Okay. So that's the beauty of Docker. And although I'm talking about Docker here, I know that depending on your setup at your institution, some places oftentimes server teams will not allow people to use Docker because of some security issues. But there is another very similar program called what? Just a second. Uh, it's not synchronicity. It is singularity. Thank you. Singularity that works very similarly and can use the same containers. Although I do not personally have experience with it because I always use Docker. Thanks, Batul. Singularity. For some reason, I have like synchronicity in my head, and singularity. Yeah. Okay. Again, we don't have the time to cover Docker today, but a recommended resource is this Carpentries workshop called Reproducible Computational Environments Using Containers. You can click on that and go to it. And one thing I do want to clear up, though, before I go forward, is I keep saying, you might hear me saying container and image, and they're really similar. But there's a slight conceptual difference, and that is that, for example, when I type this here, this is the name of an image, okay, which is defines this FastP Docker thing, right? And then when we actually run a specific instance of that, that is called the container. So you have a set image that can then generate containers, okay? But oftentimes you'll see those terms sort of used interchangeably. Okay, so where can we find these containers or images? Because it's great that we can run these bioinformatics programs, but where do we find these in the first place, right? So there's a couple sources that I've listed here: Bioconda, Biocontainers, and Docker Hub. And notably, all of the containers in Bioconda are also in Biocontainers. So you don't really need to use both. But I find that the search interface for Bioconda is a little bit easier to use. For some reason, Biocontainers is always really slow and kind of buggy. But so I'll demo how to do that here. Okay, so let's click on Bioconda. So that opens up the Bioconda web page. Woo. And you can just search over here for any software that you need to use. So again, let's going with our FastP demo, type in FastP, hit go. So it'll bring up a couple different things, but you can usually see that, some of them look a little bit differently. Like we've got R FastP, FastPhilo, blah, 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 but package FastP, that sounds good. So click on that. Now, this is the reason I'm showing you this right now is because it's a little bit confusing. It says container none, but I think that's a bug because there is a container. So if you scroll down here, it says uh, installation, and this is generic boilerplate that they have for every package, but it says use the Docker container with Docker pull, blah, blah, blah. And it says C fastp tags. So you'll notice that, again, um, this first part is the part before the tag, like I showed you over here, that we ran here, right? And then after that, it has this tag, which is a specific version. And you can click on this link to find those tags. So let's click on that link. And that'll take us to where these are actually hosted, which is this quay.io place. And it has this whole list of tags. So if we zoom in a little bit over here, you'll see that there's different past versions of fastp. So if you needed to, you could even run, again, without installing it, you can run a previous version to maybe test how that changes your output or something if you needed to. And these are typically organized by last modified, and then they have the name of the tag. But one thing to notice here is that the last modified one, in this case, it is the most recent version, but that's not always true. Sometimes you might need to rearrange by tag because someone may have modified an old tag more recently. Okay, so an old version. So do make note of that. But you're usually good with using the most recent tag. Okay, so that's how you can find containers on Bioconda. Now, one more source of containers is Docker Hub. Which is the official container registry of Docker, and you can search for content up here. And so, for example, I have a bunch of containers. This is where I store my containers. So I typed in my username, and I have a bunch of public containers. And the thing to notice is that this is sort of what, yeah, like GitHub. Like, any GitHub, as long as it's public, anybody can access these, right? And so with these containers, you don't necessarily know what's in there until you download it and have a look inside. So the containers on Bioconda and Biocontainers are actively maintained, and they're tested, and they're sort of vetted. So those are really good sources. The containers on Docker Hub could be put up by anybody with no testing. So my primary source is Bioconda, and then I might go to Docker Hub if I can't find it. But again, there you need to exercise some caution. I think Docker Hub probably does some checks to make sure there's not malicious code. I'm pretty sure, but like, again, no guarantees. And finally, if you can't find one anywhere, you might need to write your own image or container. And I often will do that if it's a really new software package that the maintainers on Bioconda haven't gotten to yet. Sometimes you'll have to make your own. And again, we don't have the time to cover that today, but there's a lesson on that in that Carpentries workshop that I linked to here. Okay. So we're moving along, building up the process here piece by piece. What we're going to do is call Docker containers from R, okay? And there is a handy package to do that called Babel Whale. And I think and so the nice thing about Babel Whale is, so we can click on the GitHub repo here, Babel Whale. And as you'll see, it can talk to both Docker and Singularity. So again, if you can't run Docker, you might be able to use Singularity. And Babel Whale has a function called run. So watch out, namespace collision. Okay, same name as function name as process_x run. So you might need to use the syntax of the double colons here to prevent namespace collisions when you use Babel Whale run, if you also have process_x loaded. So it has a similar syntax to process_x run, but it also adds the container name. Okay, so Babel Whale run has the first argument. Whoops, is the container and then the command and the arguments. So for example, we could run ls using a Docker container called, and for here, the demo is going to use a Docker container called Alpine, which is the smallest Docker container. It's like a few megabytes, which is a complete operating system in a few megabytes. It's very small. So let's go ahead and copy that and give that a try. So I'll copy that over here into RStudio. Babel whale run Alpine LSH. And it takes a second to spin up Docker, and it ran, okay? And it gave us some standard out. So, but you'll notice something looks a little bit different here, right? When I did process X run ls -h, okay, so pay attention, all right? This is what we just got standard out. If you see, this is the standard out from doing LSH in Alpine container. Now let's run it here. Okay, so LSH with process X shows us, it lists the things that are in our current working directory, right, in this targets demo. But when I did it with the Alpine, it's showing all this other stuff. So what's going on there? Why don't we get the same result? Well, that's because when we ran LSH in Alpine, it's showing us listing the current working directory in Alpine, which is the root directory of that Alpine container. So that contains a bunch of folders like bin, dev, etc., home, lib, etc., right? So these are all what's inside that Alpine container. So what if I want to run a command in this Docker container, but have it do things with files that are in my local environment? Okay, we need a way to do that, because if you don't specify that, anything that Docker does is it only sees what is inside that container. Okay. So how do you specify tags in Babel wheel? Okay, great question. So, and this is actually a feature of Docker itself and not Babel whale. We could run the same thing in the. Okay, and I'll get back to how we deal with files in just a second, but I'm going to ask this question first. It's about tags. So we could say Docker run. Now we're going to interact. I'm going to interact with Docker directly in my command line. Docker run Alpine ls.h. Does the same thing, right? That's because you don't actually have to specify the tag when you run Docker. You could also say, for example, like when we did fastp, I could say, oops, what was the rest of it? Sorry, okay. This whole part for the fastp, the part on the left of the tag, you do need all of that. That is the image name. And this, even though this has these slashes in it, those are just text. Okay, this whole thing itself is the image name. So we could do that. And when it does that, it'll automatically, oops, oh, interesting. Okay. So I guess, so if you do that, it'll automatically try to do it with a tag called latest. And most images do have a tag called latest, which is just the latest version. But it seems that the ones on Quay.io don't. And Alpine is a little bit different because it is an official image issued by Docker. And apparently you can run it without even having the latest tag. So I'm pretty sure we could say Docker run Alpine latest. Yeah, so we can give it the latest tag, but with Alpine, you don't need to give it any tag at all. But again, that's sort of, I guess, special for these official Docker images. So for Babel whale run, if we want to give it the tag, to answer your question, we would just add it here, like we do when we're running Docker at the command line. Where is my last? There it is. So we could say latest, like that. So it's the exact same as running Docker at the command line. So getting back to how we deal with files in Docker. So again, the Docker container it's a complete operating system and software package unto itself, and it's completely isolated from the rest of your environment. So we can see that in this diagram where Docker host servers could be our local computer, and then the Docker container is this thing which is isolated from the rest of it, right? But how do we get it? How do we get files to move between them? Well, you need to do that with the special argument in Docker uh, that uh, that is this dash v argument, and that's called mounting. Okay, so the mounting argument takes us a format, and again, we're using the colon here, but in this case, the colon is not a version tag. The colon specifies how to make the connection between files outside of the container and files inside the container or folders. So it's a colon, and you have two parts to it. There's a path on the left and a path on the right. The path on the left is, and this always has to be an absolute path, so starting with the slash. The path on the left is the path outside of the container that you want to connect to the path inside the container, and that's on the right. Okay. So in order to make this work, we'd have to do some, and to make this work in Babel Whale, it becomes a little bit more confusing. So here I'm doing it by getting our current working directory with the getwd function, and then I'm composing that this string using paste. Okay, and I'm not going to demo this, but trust me, it does work. But it is a little bit confusing, right? Because especially if we had multiple files or multiple folders that we wanted to mount in our Docker image, you'd have to do that for each one. And it gets just to be sort of mental gymnastics thinking about where everything is. Okay. So to make this a little bit less complicated, I've actually written a custom function to alleviate this. And I tweaked Babel Whale a little bit. So now this is getting quite custom, but I have my own fork of Babel Whale. So if you go to github.com/Joel Nitta/Babel Whale, you'll see my fork, and I'll go ahead and put that in the chat here. And I have a branch called JNFeature where I added this new function. So you can install that using remotes. So I don't think anybody has this installed yet, so you'll need to run this code yourself. So let's run remotes install Joel Nitta Babel Whale, this particular branch, okay, at JNFeed. So command run. This should go, whoops, oh, typo. That should be install GitHub. So I'll go back and fix that in the slides later. GitHub. Okay. Put that, whoops, out, and it's asking me if I want to update some packages. I'm going to skip that because I don't want to waste your time. And let me also grab the proper code to install it. I'll put that in the chat. Okay, so it installed that. So my branch includes a new function called run auto mount. And I called it run auto mount because it automatically mounts files for you. So this makes it a lot easier. We don't have to bother with this complicated code that I showed in the last slide. I am going to demo this, so I'll bring this over here into RStudio. And I'll go ahead and put this in a new R script. Okay. So what's going on here is, again, if we compare, let's compare the two versions of this ls code. So, okay, so if we say, let me see here. Okay, sorry, no, actually, I'll just do this one. Okay, so again, we need to get our working directory, getwd. Okay, so I'm going to run this getwd, and we take a look at that. So on my computer, that shows where we're at right now on my desktop. So now if I run this, Command Enter, oops, oh, I need to reload Babel Whale because now I've installed my own version of it, right? So library Babel Whale. And now I do believe this should work. Oops. Well, no, we don't need this anymore. Well, okay. Is that going to work? No. Okay, let's try again. Sorry. Issues with, maybe I'll restart my R session too. Okay. So this can get a bit confusing if you have multiple versions of a package, if you've tried to install a package from different sources. Let's make sure this works. Run auto mount. Okay, there. So it shows the help file. So now we know that we're using my branch. So now if I do this again, grab the working directory and then run auto mount, now it does show us our files that are in our actual local working directory and not the working directory of Alpine. Okay, and so the way and what's going on, the difference between the Babel Whale run and my Babel Whale run auto mount is this arg's argument, which is the exact same in that it takes a character vector. But the only difference here is that whenever you use a local file, you name it. All right. So this is let's look what is this. Okay. So if we type C, this function here, or this command here, this is a character vector, and some of the elements of the vector have names. Okay. So the local file or the local folder is named file, and the next one doesn't have a name, it's just H. But the way this run auto mount works is if one of these are named file, it knows that is a local file, and it will take care of the mounting for you automatically. And maybe a thing that you may not, if you don't name your character vectors very often, which typically you don't need to, we can assign. You always assign names with this equal sign, right? So a equals 1. You can actually assign the same name to different values in the vector, right? So we have a vector of 2 numbers, and they're both named a. So R doesn't care. You can name multiple things, the same name with files. So I'm just using that as a way to tell Docker that this is a local file. And then it'll know, well, to tell Babel Whale that this is a local file, and then it knows to do the mounting. Okay. So this can greatly simplify running commands on local files. So this is an example of how we can use auto mount, this run auto mount function, for example, to run FastP. So I'll go ahead and copy this code and demo this in RStudio over here. Okay, so we're going to use base R to download some files. These are actually test files from the FastP package or program. So command R or command return to download those two. So if we look at our files now, we have r1.fq and r2.fq that came from GitHub. So now I'm going to run this run auto mount, and you'll see we give it the container name, then fastp, the command to run, which is the fastp program, and then the arguments. And I don't have time to go into the details of fastp, but it's like many other bioinformatic command line programs where you have these series of arguments that are really short names that have these dashes, right? So this is dash lowercase I is the one read input, dash uppercase I is the reverse read input, dash O is the forward read output, big O is the forward read or reverse read output, and then a report file. So I'll hit Command R to run that. So now it's running. Thanks. And we get the output from the standard error from process X run. but you'll notice that it also issued out these files over here. So now we have our trimmed file and a trimmed read report that we can actually view in the web browser. So this is running FastP on these demo files. So again, now we have run FastP from R without installing it ourselves, using local files, without bothering with all the mounting. Okay. So I hope you see where I'm going here. Okay. The next step, now that we've done this with Babel Whale, is we can actually define a function that kind of hides some of that complexity away. And I'm calling that trim reads. Okay. So again, I'll demo this. So we'll copy this here and paste it over here. Oops, over here. Okay, so FastP wrapper function. So this is a custom function. Now this is the function that I would use in a target's workflow. So it's called trim reads. It's got several arguments. So forward read in, reverse read in, and then the output. So these are the inputs files, and the output files are forward read out, reverse read out, and a report. And we'll run that. And this is just wrapping that Babel Whale call within a function, right? And a key thing to notice here is that the output, the reason that we do this, right? If we had just run this with Babel Whale, it would return this output, which is a list, including the standard error. But when you're running this as part of a target's workflow, it's really important that we always are keeping track of these file names. So that's why we need these wrapper functions. So the output of the wrapper function is going to be the path of the output files. Okay, so we'll hit command return to define that function. And now we can run this, and it also makes it much prettier, right? Because we can say trim reads r1.fq, r2.fq. I could even give the output a different name. Because we're going to run it again. FU doesn't matter, but okay, and then hit command return, and now it's running that function that we just defined, and it returns the path of the output that it generated. Okay. All right. So again, these are all these building blocks that we're putting together so we can do all this in a target's workflow. And yeah, there's an example of running that function. So that is most of the pieces that we need. And the way that this works to do a bioinformatics workflow is I will have my two files, functions.r and targets.r, and my functions.r file is going to include all of these wrapper functions that are calling Docker from R. And then I chain together all of the input and the output in targets.r. And the really important thing is that to build all of these targets, I don't use the tar target function, I use the tar file function. And that's because tar file is under the hood, it's calculating the hash of each of these files, and it knows if anything has changed. So that's how we can link them all together and track their dependencies. And so this is an example. I'm not going to run this right now, but this is an example from the VCF workflow that is doing converting a SAM file to a BAM file using. Whoa. Sorry. I forgot. I can't scroll left and right there, or it would make my. Anyways, okay, there we go. So this is using this SAM tools Docker container and converting a alignment SAM file to a BAM file. Okay, so that's just one step in a long step and a long series of steps in a workflow. Okay, so and I'm at the end. I am gonna demo that workflow so you can see that in action. All right. So an important part of reproducibility is maintaining your computing environment. And although a lot of the emphasis of the talk today has been about targets and using targets for code automation, for bioinformatics workflows, we also want to uh, maintain all of our package versions, right? So, and Docker is fantastic for maintaining package versions of these external software programs that we're calling from R. But then we also need to somehow maintain our version of R, right? So how can we do that? Well, normally I would use Docker itself to run R, but we can't. It's sort of against the rules to to call Docker from within Docker. It's just generally really sketchy in terms of security. Um, so my solution for doing that is to use conda and rinf. Okay, so what is conda? Again, this is another thing where we don't have the time to get into details, but conda is an open source package management system, and it was originally created for Python programs, hence the snake-ish title, but it can package and distribute software for any language. And in fact, there's conda distributions for R, which we're going to use. And if you want to learn more about the details, again, my go-to is Carpentry's workshops. So there is another Carpentry's workshop on Conda specifically. So the way Conda works is if we use a YAML file, which is YAML is a very simple markdown language to define software. And so we give it, and this is what the example YAML file looks like for one of my targets workflows. We give it the name. Channels are places where it pulls down code, and then dependency is what actually goes in there. And the dependencies is R, including the rinf package, because we're going to use rinf to manage R packages, and we're specifying that is at version 0.15.5 of rinf. Okay, so that comes both with R and rinf. And we can build this environment by using the conda inv create command. So we'll do conda inv create -f, and then the -f argument takes that YAML file. So that'll build this one called bioinfo example inv. So I'll just go ahead and run that over here. Copy this. And I already have this. I've actually already done this before, so it'll give me an error if I try to tell it to do it again, unless I say force. So I'll do that. Oh, excuse me. I forgot, I don't have my environment YAML here. Where do I have that? Well, we'll go ahead and copy that too. And use handy RStudio to make a new file. Text file, and save this. Just a second. Run int.yaml, and okay, cd targets demo, and we'll try that again. Oh, I added the A, I think. All right, YAML. Okay, so this is what the output of conda looks like when you tell it to build an environment. Well, nothing yet because it's thinking. Okay, and now it started off. And so it is going and downloading packages and installing them into a custom environment on your computer. Now, a conda environment is sort of like a Docker container in that it's isolated, and it includes all the dependencies that need to run the one thing that you've told it about, which is rinf, right? But it's a little bit different from Docker in that it sort of sits, you can think of it as sitting on top of your current environment. So it will have access to other programs that are on your local machine, as well as whatever it's installing. Okay. So it can call Docker, whereas you would not want to try to call Docker from Docker. Okay. So I'm gonna go continue through my slides while that's going because it takes a few minutes to think about it. But once that's built, you could then enter the environment by running the conda activate function, or excuse me, command. Conda activate, and then the name of the environment, which we specified in that YAML, right? So here's the name of the environment. So you'd run conda activate, for example, bioinfo example env, and then we'd be inside there, and it will have that version of, and that will have R and renv in it. And then when we're done, you'd run conda deactivate. And so if I were to do this, this is what it would look like. So you'll see conda activate, and you'll notice that this thing on the left here will change from base, which means you're not in a conda environment, to the name of the environment that we're inside. Okay, we'll come back to that later. All right, so that's conda. Now, again, I'm using conda to maintain a specific version of R, and that version of R comes with a package called renv. So renv is a package manager that maintains R packages, and it does so, and I have a link to it in the slide here, and it does so with a file called renv.lock. And again, this is very similar, analogous to the conda environment.yaml file. And so, for example, this is what one portion of that might look like. And you don't generally touch this by hand. It's only renv will edit it, generate and edit it for you. But this is for the matrix package. And it tells us the version and where it came from and its hash. So with that information, you can install the exact same set of R packages on a different computer or a different location. And so these are some of the basic functions to run renv. You initialize it in a particular project with renv activate. You install all of the packages with renv restore, and you can update that package list with renv snapshot. And the snapshot always saves it to this renv.log file. And my recommendation is to track that with Git. And that way you can always document what package versions you're using. Okay, and another really important point here that I didn't mention before about targets is that all the targets does track of course, your target workflow and all of your functions. It does not track package versions. So if I use a function in my workflow, say a function from tidyverse or something, and then or say like ggplot, and I update my ggplot package and I rerun that code, targets doesn't know about that. If it's a function from an external package and that function changes, it will not track it. It will not know to rerun it. So that's why it's really important to use renv or a package manager so that you have all of your package versions documented alongside your targets code. Okay, so we're finally getting to the actual bioinformatics part of it, and this is where we're going to put all of this together into a demo workflow, which does some variant calling. So this is actually based, again, I love carpentries. This is based on a data carpentries genomics lesson. So let's take a look at that. All right, so I'm going to click on this link, and I'll copy this into the chat as well. So you should all check out, to understand what the workflow does, please have a look at the carpentries lesson here. So this is a variant calling workflow for E. coli. And so it's actually part of a longer series, this data wrangling and processing for genomics. So if you wanted to get even more context, you could back up a little bit and see about information about what is this experiment, things about trimming and filtering, etc. But we're starting at number 4, which is variant calling. So it says that we're doing a long-term evolution study of E. coli, and we have a population that we're tracking, and we want to see how this population changed relative to its original population, this E. coli strain rel 606. So what we're going to do is compare reads between this population, this later population that has evolved, to the reference population. So we need to align reads to the reference, which is going to output a SAM file. Then we convert that to a, so here's the alignment, which is going to convert, and then we need to convert that SAM file to a BAM file and sort it. And then once we do that, now we're ready to do the variant calling and see what specific bases changed. And that's going to output this VCF file. So you can see there's many different steps here. And if we were going to do it the way it's described in this Carpentries workshop, you'd be doing all of these steps manually at the command line. For example, VCF tools call, blah, 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 VCF utils.pl, etc. And you would need to have installed all these packages yourself by hand and type all these commands yourself by hand. And so none of this is reproducible. So what I've done is converted this into a reproducible targets workflow. So, and I put that in this repo here. So again, I'll copy this into the chat. And we'll click on that. Open this up over here. So this is the example workflow using targets, and it's based on this. And I have some information about how you can run it here. So we're going to go ahead and do that right now. So I have that information here, but it's also on the slide. So I'll back up to the slide. So let's run these commands, okay? I'm going to move this to the side a bit and bring this up over here. So I'm just going to go ahead. Oh, our example conda finally finished, but we are going to be doing the same thing right now, so I won't worry about that. Okay, I'm going to go ahead and change back up to my desktop, which is probably a good place for you to do it too, so you can find everything. And I'm assuming everybody has Git installed. If you don't, just think of this as a demo and a non-interactive demo, and you can go back and try it once you have Git installed. So we'll first do a git clone to copy this folder. Okay, so that's cloned the targets VCF example. So if we can now move into that folder, cd targets VCF example. And now we're inside that folder. We can do a ls to have a look around. We see our targets.r, etc. And this contains the environment.yaml that we need to build the conda environment. So we can do that with conda env create-f environment.yaml. I'll run that right now, but it's going to give me an error because I've already built this. So I'm not actually going to do that myself just to save us some time, because conda will have to do everything over again. But when you run that, it should actually run it, and you'll see output like we saw earlier with all this solving environment, preparing transaction, etc. Okay, so that would install that. And once that's installed, then we'll activate it with conda activate vcf-example-env. Thanks for a second. Just takes a moment there to load. Okay, there we are. And now you see that base has changed to VCF example env. So we are now inside that environment. And I didn't demo this earlier, but if we were to type, so before we type the next command, I'm just going to show you to demonstrate the reason we have this environment is because it contains R, right? So if we type R, you'll see that we are at inside the um, R. Uh, we're inside our console, and because of the way I've set up this GitHub um, folder, it includes some information about um, RInf. So, boy, see, this is what happens when you go off script. You get errors. We don't have to worry about that. Um, but this was just to show you that now we are actually in R. So if we were to say, print hello, it would do that. Um, but I'll exit R, and we're going to continue working directly from the command line. Okay. So going back to the script, the next thing you should actually do is use a command called rscript. And so what that does is, this is just a convenience so we don't have to go into R manually ourselves. This is going to tell R to run this command, the rm restore command, from the command line. So rscript -e rm restore. So the rm restore function is going to install all of the packages that we need to run this. And it's going right now. And this actually should not take too long on my computer because rm has a catching mechanism to copy file folders that or packages that you've already installed somewhere else. Well, we'll see how long it takes. And is everybody able to do this on your own computer so far? I hope. And just to show you again what's happening kind of under the hood here is, if we look at the GitHub repo, we see all the files in here. It includes both environment.yaml. So environment.yaml is the one that is used to build the Conda environment, and it includes rm.lock. And rm.lock is what is doing right now, that is going through and installing all of these R packages. And there's a lot. And it seems like it is actually downloading everything. So that is taking a little bit longer than I expected. So bear with me here. But I can also go in and show you some more of what this looks like on the inside here. Let's see here. Let's take a look at the underscore targets.r file. So this is what the targets. This is the targets version of that data carpentries lesson, right? So as before, we load our packages and functions from those files. This is actually a bit advanced. You can have a look in the targets manual about how to set up parallel backends, but this is needed to run targets in parallel. So, and this is a good one to use. The caller backend is good to use for local, on your local machine. But if you are running this on a server, yes, it does support job scheduling for HPCs. So if we go to the targets package manual, Google, and you scroll down a little bit, this is the targets R package manual. Again, this is like the Bible for targets. It's really useful. It has chapter 13, high performance computing. So if you click on that, it goes into detail about how you can do that. And there's a couple different backends you can choose from, and different ways you can set up the workers, which are those parallel instances. And essentially what this can do is it can build each target as a separate job on the cluster. So yeah, that's pretty nice. Okay. Let's see. So I've actually taken some shortcuts to make my code a bit smaller by instead of typing these same paths over again and over again, I set up variables for the data directory, intermediates directory, and then the final output directory. And I use the fs package to construct paths. So like I download and unzip this genomic reference genome, or the reference genome, to the data directory in a subdirectory called ref genome. Okay, and so again, you'll notice that most of these use the tar file. Some of them do use tar target if it's not a file, but most of them are files where it always is going to result in a file. So when I run this, oh boy, that's going to take a little while. I do have this all installed and set up somewhere else, so I might just switch into that instead of letting RMV install all these by hand or over again. Yeah, I'm going to do that. So just bear with me for a second while I open up a new project. Project and new session. Where do I have it? Oh no, oh no, can't find it. Was that it? No, that wasn't it. Okay, I'm sorry. This is taking longer than expected. So I will continue to explain it over here in the GitHub. So what's going on is, yeah, for example, we have this download, and this is a custom function that I wrote, download and gunzip, which takes a URL and then spits out a FASTA file as output, right? So that's the reference file. Similarly, we have one that's going to download the trim reads because they've made the trim reads available to us. We didn't do the trimming here. So those are the trim reads. And so eventually, so download those. I have a function that indexes the reference genome using BWE index. And again, so for example, like, yeah, this one, in this reference genome, the input is the reference that we so E. coli ref, which is the same thing here, E. coli ref, right? So that's the one that we downloaded. And then that's used as input in another step, which is indexing the genome. And that's going to result in a output object called E. coli ref index, which itself is pointing to this file, right? Which is in our data directory. So I hope this makes sense where, man, I'm sorry about this. I thought this would go faster. Where did I put that? Let me see if I can find it one more second. I'm just going to try to find it again because it would be nice if we can actually see this. I'm not finding it. But basically, each one of these objects itself is actually just a pointer to a file that we specified with tar file, and then we can use that as input into the next step. So for example, we have BWMM, which is the aligner that is going to align the forward reads and reverse reads to the indexed reference, et cetera, et cetera. And so it'll go through and do each of the steps in that workflow, and I have it commented so you can see what's going on. Convert SAM to BAM, then do the variant calling, and then at the end, what I always like to do is render a report that shows us what happened. Okay, and so that's here in this report.rmd. And just to illustrate how that works, if we go back up, report.rmd, I have in the, yes, in the doc folder. And you'll notice, so this is a R Markdown report. And you'll notice there's a call here to tar load. Okay, so what's that is doing is loading an object from the target's pipeline, and then we can use that to give a summary of our workflow. And when you render a report using targets, it's always important to use the tar render function. So let me show you what that looks like. Underscore targets. So I'll scroll back down here. So again, this is another flavor of the tar target function. This is called tar render. And it's a special function that knows that that this target is actually an R Markdown report. And so it knows to do that last after the other targets are built. And it knows that it depends on that we've called tar load here, and it depends on this target object. Okay. So if filtered variance change, if this object filtered variance tibble changed, it would know to rerun the markdown the R Markdown document. Yes, and I think what was I was going to say one more thing. I can't remember what it was. Okay, are there any questions at this point? Yeah, and I apologize. Unfortunately, the RF restore, I should have just started that at the beginning of the workshop. It is not using the cache like I expected it to. But please, everybody, do run those commands that I've shown you here in the slides. And you should, when that's done, you should see the HTML report get built in the output folder, which is targets user results. And by the way, this is what I do for my research. I use R Markdown to generate the paper that I then submit to a journal. So it's all reproducible and it flows from code. And yeah, again, the best way to learn this is to do it yourself. So do please try to follow to use these commands here and clone the workflow example and have a look at that code and see what's going on there, so you can understand how that all works. So yeah, and we do have about 5 minutes for questions. So if anybody has any questions, please. And there was a question at the beginning about SnakeMake, and again, I can't speak to that much personally because I just haven't used it. I'm an R guy, so I haven't tried SnakeMake, but so it's really hard for me to give an objective comparison. And things, I don't know, things may be easier to do there, but this is I think the advantage of doing this is that it works well if you already have existing R code and R workflows. This is a way to run those external programs within R. So that's why the biggest reason I would recommend it.